Hello everyone, hope you all are doing good. I am Anjana from Learnohub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 10 Physics Chapter 12 Radioactive. We will be discussing the topic changes in nuclei during alpha, beta and gamma emission, uses, sources and safety measures of radioactive substances. We will be also discussing about the background radiation. Hope you all are ready for the session. Let's begin. By now we have understood about radioactive substances. These radioactive substances are unstable in nature. Okay, so these unstable radioactive substances should be made stable. Yes, so they become stable by emitting some radiations. These radiations like alpha radiation, beta radiation and gamma radiation, when emitted from their nucleus, what happens? They come to the stable state. Okay, when alpha and beta radiations are emitted or alpha and beta particles are emitted, there will be a change in the number of protons and neutrons. Okay, but when it comes to the gamma radiation, when gamma rays or gamma particles are emitted, there is only change in energy. There is no change in the number of neutrons or protons, only changes in the change in energy. All these are nuclear changes. Okay, these are called nuclear changes. So, from the unstable state, the substance comes to a stable state by emitting alpha, beta or gamma radiations. Okay, unstable radioactive nucleus undergoes spontaneous decay by the self-emission of alpha, beta and gamma radiations to form a stable nucleus. Clear? So, this is a nuclear change. First, let us understand alpha emission. In alpha emission, which particle will be emitted? Alpha particle will be emitted. Okay. Here, consider a radioactive substance or an element which we represent by X. Okay. ZA, where Z is the atomic number and A is the mass number. So, here, this particle is undergoing alpha emission, which means it is releasing out an alpha particle. What is alpha particle? Alpha particle is a helium atom. Okay, with atomic number 2 and mass number 4. Here, mass should be conserved. Okay, you can see that this is A. Here we have 4. Let's say a new element is formed here. Okay, whose mass number will be A minus 4. Okay, if this should be balanced, A minus 4 plus 4 you will be getting A. What about this place? Here you should have Z minus 2. Z minus 2 plus 2 is Z. Okay, so here one alpha particle is emitted. Many such alpha particles when emitted, many helium atoms when emitted, we call it alpha rays or alpha radiations. Okay, alpha rays. So this is the parent nuclei. And this is daughter nuclei. Okay. Now you will be able to see that when you compare the parent nuclei and daughter nuclei is having atomic number 2 less than the parent nuclei and mass number 4 less than the parent nuclei. Okay, here the particle that comes out is having 2 protons and 2 neutrons. We know mass number is number of protons plus number of neutrons. Yes, so here 2 protons plus 2 neutrons, 2 plus 2, 4 is the mass number. So, a particle with atomic number 2 and mass number 4 is released, which is an alpha particle. Now, let us take an example. So, here we have taken X as the parent atom and Y as the daughter atom. We will be taking uranium. Uranium 92 is the atomic number, 238 is the mass number. Okay, it is undergoing alpha emission. An alpha particle is released. Then, what will be the daughter nuclei? Which will be the element that comes over here? You will be able to see that the element will be having a mass number 234. Why? Because in alpha emission, what happens to mass number? Mass number decreases by 4. Okay, what about the atomic number? Atomic number should decrease by 2. Here we have 92. Atomic number will be 90 and the element is thorium. Okay, so uranium 92-238 undergoes alpha emission. It releases an alpha particle and you get daughter nuclei is thorium 90-234. Okay, this nuclei which form will be having properties, or this element will be having properties that comes 2 elements before in the periodic table of uranium. Okay, before uranium 2 elements front, when you go in the periodic table you will be finding an element and that element will be having properties similar to thorium 90-234. Understood? So this is all about alpha emission or alpha radiation. If an unstable nucleus contains much more neutrons than the number of protons, it may emit particles containing 2 protons and 2 neutrons tightly bound together known as alpha particle. So remember one more thing here, for alpha emission to happen. So we know that we have already discussed that when the atomic number increases or it goes beyond uranium or near to uranium, the number of neutrons will be higher than the number of protons. Okay, in those cases they come to the stable state by emitting alpha particles. Next is beta emission. Here the particle emitted will be a beta particle. What actually happens is, in this case also, when the number of neutrons is greater than the number of protons, what happens is a beta particle is emitted. Now what is a beta particle? Beta particle is nothing but it is an electron. So here what happens is a neutron changes into a proton. Okay, for example, neutron. This is how you can represent a neutron. This neutron changes into proton and then there is an electron. This electron is called beta particle. Okay, beta particle emission happens. With this, for the law of conservation laws to be followed, another particle will also be emitted, which is represented by nu bar, and this is called antineutrino. Okay, it has no charge and the rest mass is 0. Okay, this particle will also be emitted for the conservation laws to be done. Okay, now for example, if you are taking a parent nuclei X, Z, A. Okay, here you can see a neutron is changing into a proton, which means the number of nucleons will be the same. Yes, number of nucleons is not changing, which means the daughter nuclei formed will be having the same mass number. Now what about the atomic number? What is atomic number? Atomic number is the number of protons. So here what is happening? A neutron is changing into a proton, which means the number of protons should increase by 1. Okay, so it becomes Z plus 1. And then the particle emitted is beta particles, which is having, in place of atomic number, it is -1 and mass number place you will be having 0. Okay, so this is an example of beta emission and the particle, this particle emitted is called a beta particle. Clear? We'll take an example. When you take radioactive carbon, okay, carbon 614, atomic number is 6, that is number of protons and number of electrons is equal to 6. What about mass number? Mass number is 14, which means the number of neutron is equal to 14 minus 6. Atomic number should be subtracted from the mass number to get the number of neutrons, that is equal to 8. Okay, it should come to the stable state. So here what happens is one neutron will change into a proton, which means for the new element formed, the mass number will be the same because the number of nucleons are the same. Okay, it will be 14. Now what about the atomic number? Atomic number should increase by 1. It becomes 7. Okay, and the element is nitrogen. Nitrogen 714, this is in the stable state. So the carbon which is in the unstable state comes to the stable state. And here the particle emitted, beta particle, -1, 0. Okay, so this is beta emission. So comparing beta emission and alpha emission, we'll understand that in the alpha emission, both atomic number and mass number is changing. But when it comes to beta emission, the mass number is the same, but only the atomic number is changing. So here what happens is, when you check the periodic table, the new element formed, Okay, the new element will be at a place after the original element. Okay, in the previous case, in alpha emission, we have said 2 place before the original element. So here, properties of the element will be to the element that is just next to the element that is considered. Okay, this is all about beta emission. When an unstable nucleus contains neutrons more than the proton, a neutron may change into a proton by emitting an electron. And here this electron is the beta particle. Now the third one is gamma emission. So we have understood what alpha emission and beta emission is. In case of alpha emission, there is a particle released which is alpha particle. In beta emission, an electron or a beta particle is released. So here when you come to the case of gamma emission, there is no such particle released, but a radiation is released which is an electromagnetic radiation. Okay, a gamma ray photon will be released. Now why this is released? Let's see. Okay, so when you take an element, okay, an element X with atomic number Z and mass number A. Okay, it is in the excited state. The excited state we represent with a star here. Okay, from this excited state, it should come to the ground state. For example, if the parent atom is in the excited state, it should be taken to the ground state. To bring it to the ground state, so same XZA, that is atomic number or mass number is not going to change, but the star will be removed, which means it is now in the ground state or the stable state. It has come from the excited state. Excited state means there is excess of energy. This excess of energy when released, only then it can come to the stable state. So this excess energy comes out as gamma radiation. So this gamma radiation, atomic number and mass number, that will be 0. Which means you can see here that mass number is not changing, atomic number is also not changing. Which means that the nuclei, inside the nuclei there is no change happening. The same nuclei is there. Only thing is there is a release of energy as gamma radiations. Okay, or as a gamma ray photon. Now this gamma emission does not actually happen a lot. It is followed by an alpha emission or beta emission. Either after alpha emission, it will be followed by gamma emission, or after a beta emission, to bring it to the stable state, gamma emission will occur. Okay. Now one more thing, alpha and beta emission will not happen simultaneously. Either alpha emission or beta emission. After alpha and beta emission, what can happen? A gamma emission can happen. So understood? Effects on atomic number and mass number due to alpha, beta and gamma emission will compare and study. First here we have the atomic number given. Z represents atomic number and A represents mass number. Also, atomic number is number of protons or the number of electrons. Basically, we will take it as a number of protons. What about the mass number? Number of neutrons plus number of protons is the mass number. Okay. During alpha emission, what happens? During the alpha emission, atomic number, here an alpha particle is released. Therefore, atomic number decreases by 2. What about mass number? It decreases by 4. Okay. Decrease in both atomic and mass number. Clear? Now, during beta emission, what happens is increases by 1. What atomic number? It is increasing by 1. What about the mass number? There is no change. Okay, there is no change in the mass number. Here, what is happening? A neutron is changing into proton. So, actually, this electron is not created from the, you know that an electron is being released. This electron is not created in a nucleus. Inside a nucleus, an electron cannot stay. So, here what happens is during the decay of a neutron to form a proton, an electron is being released. Okay. Now the third one, during gamma emission, there is no change in the atomic number nor the mass number. Okay. This gamma particle, they are having no mass or charge. Clear? So this is about gamma emissions. So important points to remember. One we have said, that is about the electron. Electron is not formed inside the nucleus. Okay. Just during the decay, this particle is being emitted. Next, an important point is alpha. After alpha and beta emission, what happens? Gamma can be emitted, okay, to bring it to a stable state. It's not necessary that after an alpha emission, what the element that you get is stable. Okay, sometimes you will have to do it again, that is again an alpha emission. So this process will continue until a stable nucleus comes. Okay, so the parent nuclei will first decay by gamma emission. After that, the continuous alpha emissions can happen, and after that it can come to a stable state. Clear? Uses of radioactivity. So we have said that when the atomic number goes greater than 82, in that case you will be able to find radioactive substances. Even when the atomic number is less than 82, there are some elements, there are some radioisotopes existing. Okay, let's see, for example, when you take carbon, okay, carbon 614 is a radioisotope. The normal carbon or the stable carbon is carbon 612. Okay, so here you will be able to see that the number of protons is equal to 6 and the number of neutrons is also equal to 6. So the mass number 6 plus 6, 12. Okay, when you take this case here, you will be able to see the number of protons is equal to 6. That is the atomic number. What about the number of neutrons? Here we know that number of neutrons plus the number of protons will be equal to the mass number, which is 14. Okay, number of neutrons plus 6 is equal to 14. Number of neutrons is equal to 14 minus 6, that is equal to 8. Okay, number of neutrons is 8, which means the number of neutrons is greater than the number of protons. So when the number of neutrons becomes greater than the number of protons, it is a radioactive isotope. So this is an example, carbon 614. Next, potassium. Next is potassium 1940. So here you will be able to see the number of protons is equal to 19. What about the number of neutrons? Number of neutrons is equal to 21. Again, the number of neutrons is greater than the number of protons. So this is also an example of a radioisotope. Okay. Next example, when you take cobalt 2760. Here the number of protons is 27. What about the number of neutrons? Number of neutrons is 33. So this is an example. When you take phosphorus 1532. Here the number of protons is 15 and the number of neutrons is 17. So this is also an example of radioisotope. Okay, either these types of radioisotopes exist or you can form the radioisotopes because there are many uses of radioactivity. So these are formed by nuclear transmutations, by alpha, beta, gamma, radiation emission. These can be formed. So basically the three places where the radioactivity is widely used are, one is in the medical field, okay, medical use, then the scientific use, and then the industrial use. So we'll be discussing them in detail now. First medical use is in the use of radiotherapy. So what is radiotherapy? In case of radiotherapy, gamma radiations are used. Okay, that is cobalt 60. Cobalt 60, atomic number 2760 is the mass number. Here the number of protons is equal to 27. Number of neutrons is equal to 33. Okay, number of neutrons is greater than the number of protons. These gamma radiation is allowed to pass through the skin. So we have studied about the penetration power when we studied the properties of alpha, beta and gamma radiation. So penetrating power is maximum in case of gamma radiations. Okay, we have seen that the alpha radiations can not pass even through the skin or a piece of paper. Maybe it may pass through a piece of paper, that is a thin sheet of paper. But you have seen that the gamma radiations can easily penetrate through the skin, okay, and damage the cell. So here, in case of tumor, if a person is having cancer, you know that there are tumor cells. So these tumor cells can spread easily, okay, they are widely spreading. So these should be destroyed. For that purpose, gamma radiations can be used. So this is called radiotherapy, in which the gamma radiation, they are targeted to the tumor cells and these tumor cells are killed. Okay, so in diseases like leukemia and cancers can be treated using the radiotherapy. Okay, that is the cells can be removed. That is the tumor cells can be killed. Okay. Next medical use is to detect the brain tumors and blood clots. So here what is used is weak salts of radioisotopes. One such salt is radiosodium chloride. Radiosodium chloride. Second, radioiron. Third, radioiodine. These are called tracers. Okay. Now what happens is, these salts, for example, radiosodium chloride along with the common sodium chloride is injected into the body, okay, into the blood. Then the radioactivity at the different body parts, different blood points are then studied, are then noticed, and this difference is studied, okay. So this process is called radiocardiology. Radiocardiology. Okay, so using this method, before the tumors or the clots it becomes dangerous, they can be removed, or that is proper treatment can be given and removed. So as these are used as tracers, before it becomes dangerous, they helps to cure using the detection, using this method of detection. So next medical uses, gamma rays emitted by the radioisotopes are used to sterilize bandages, dressing, syringes and other equipments to make them free of germs. We know that in a hospital, they won't be using the same scissors without cleaning them on a different person which is used for a person. Okay, why this is not done? Because there is a chances of spreading of germs. We know how in hospitals the diseases get spread. Okay, so we have to clean these. Okay, they should be sterilized. For that, either they can do, one thing is hot water bath. That is, in hot water all these can be kept dipped for some time, and using disinfectants it can be cleaned. A more easier and safer and reliable method, this is a cheaper method, is to use the gamma rays. So here inside a chamber all these equipments are kept. Okay, then the gamma rays are passed. So what happens when gamma rays are passed? These are all metal equipments. Okay, so these gamma rays will help to kill the germs. Okay, they will pass through the germs and they will be killing the germs, and then this equipments can be further used. They are sterilized. Okay, a scientific use, alpha particles emitted from the radioisotopes are used as projectile for nuclear reaction. We know what an alpha particle is. Helium-2-4. Here it contains 2 protons and 2 neutrons. Okay, now what happens during an alpha emission? We know what is happening. Alpha particle is being released. These alpha particle released will be made to bombard with an atom. Okay, and the reaction can be studied. Okay, so here using this you can study the size of the nucleus and also about the different nuclear forces. For that purpose this alpha particles can be used. Okay, and also in the nuclear fission reaction, we will be studying about nuclear fission reaction in details. So these alpha particles emitted can be used helpful in the fission reaction, nuclear fission reactions. Next is the radioactive tracers are used in agricultural science to study the growth of plants. We have said that these radioisotopes can be used to study about the tumor cells and the blood clots in the human body. Similarly, in case of plants, also the study, farmers can make the study. That is, how the water intake is, how about the growth of the plant can be studied, how much water intake is there, about it at the different parts of the plant. Is the phosphate atoms reached? So, is there proper nutrients reaching? When you use a chemical fertilizer, is this chemical fertilizer useful, or is it reaching every part? All these can be studied. For this purpose, the main isotope that is used is phosphorus 1532 or phosphorus 32. Here we know that the number of protons is 15 and that of neutrons is equal to 17. Okay, this is a radioisotope. This radioisotope can be used in the study of the growth of plants. Okay, if the sufficient phosphorus is not there in the plant, it can be supplied. If there is excess, it can be removed. For all these purposes, this radioactive tracers can be used. Next scientific use is carbon dating. In carbon dating, an isotope of carbon 614 will be used. So here when the neutrons hits the nitrogen atoms, we know nitrogen atom is N714. When the neutrons hit, it will be forming an isotope of carbon which is a radioactive isotope carbon 614. Okay, so we can study the age of archaeological importance, some materials of archaeological importance, buried plants, then the skull. From this, the age can be calculated. Of the different substances, age can be calculated. So here what happens is this carbon 14 will decay. Okay, they will emit beta radiations. Okay, beta radiation, that is beta particles will be emitted. Okay, so when the carbon 614, okay, it emits a beta particle, that is a beta particle, again nitrogen 714 will be formed. Okay, so in 5,730 years, what happens is the amount of carbon-14 present will reduce to half. Okay. If initially some amount of carbon-614 was present in, for example, the skull, after 5,730 years, it reduces to half. So, this is a half-life. Okay. Next, when you take it after 11,406 years, it would become 1/4. Okay. And 17,190 years, it becomes 1/8. Okay. So, finding the amount of carbon-14 in the material, we can see how old it is. Clear? So, after many years, what happens is the carbon-14 will get completely decayed. Okay? It won't be present. In that case, you won't be able to say how old the substance is. So, this many years it can be determined. So, this 1/8, then it becomes 1/16, then it becomes 1/32. Okay? As the number of years increases, the chances that we can find the age of this material is also decreasing. Okay, this is what carbon dating is. Here carbon-14 isotope of carbon is used for the study to understand how old the substance is. Okay, mainly it is used in the archaeological studies. Next, how radioactivity is used in industries. Radioisotopes such as uranium-92-235. This is the radioisotopes are used as fuel for the atomic energy reactor. So, the atomic energy reactors working, what is helping? Uranium-92-235 is a fuel. It is a fuel that is used in atomic energy reactors. Second point, radioisotopes are used by engineers in factories to avoid the accumulation of charge on the moving parts of machine due to friction. So, when machines are moving, we know that due to the wear and tear, frictions will be created. Okay, friction lead to wear and tear. So, to prevent this, that is, accumulation of charge can be removed using the radioisotopes. Okay. This is why in factories engineers use the radioisotopes. Next, the third point, the ionizing effect. We have studied about the ionizing power and the penetrating power. Ionizing power is maximum in case of alpha radiation and the penetrating power is maximum in case of gamma radiation. So, ionizing effect of radiations from the radioisotopes is used in making certain luminescent signs. Luminescence also we know that is a glowing effect. Okay, for this to produce some luminescent signs, the ionizing effects of the radiations can be used. Now, the fourth point is knowing the penetrating power of beta radiation emitted from radioisotopes. They are used to control the thickness of paper. This also we have studied. Penetrating power is maximum in case of gamma radiation. So, we can control the thickness of paper, or while during the manufacture, the thickness of paper, plastic and metal sheets can be done. That is, it can be manufactured in whichever way we need by using the radiations. Okay, mainly the beta radiation. So, beta radiation's penetrating power is between that of alpha and the gamma radiation. It is greater than the penetrating power of beta radiation is greater than that of alpha radiation, and it is less than that of gamma radiation. Gamma radiations can penetrate very deeply. Okay, alpha radiations cannot penetrate that easily. Okay. Even it is not necessary that when you take a thick cardboard, the alpha radiation can pass through it. We have already discussed the properties of alpha radiation, where we have explained in detail about its penetrating power of different radiations. Let us now take an example. One isotope of uranium has a mass number 235 and atomic number 92. What is the number of electrons in the neutral atom of this isotope? Neutral atom of uranium isotope, it can be represented as uranium 92 235. So, how to find the number of electrons? We know that the number of protons is equal to the atomic number, and that is also equal to the number of electrons. So, normally we say the atomic number is the number of protons inside the nucleus of an atom. So, this is also equal to the number of electrons, because there should be a charge balancing, number of positive sign. The positive charge should be equal to the negative charge for a stable nucleus. Okay. So, here you can find the number of electrons easily. What is the number of protons in this case? It is 92, because atomic number Z is equal to 92. So, number of protons is equal to 92, and hence the number of electrons is also equal to 92. So, here the answer is 92. Now, the second question, what is the number of protons and the number of neutrons in this nucleus? We have already got the number of protons, which is equal to the atomic number, which is 92. Now what about the number of neutrons? How to find number of neutrons? Number of protons plus number of neutrons will give you the mass number A. So here the number of protons is 92 plus number of neutrons will give you the mass number, which is 235. So number of neutrons is equal to 235 minus 92, which is equal to 143. So here the number of neutrons N is equal to 143. Okay. Now the third one, do all isotopes have the same number of neutrons? So what are isotopes? Isotopes are elements in which the number of protons will be same. That means atomic number will be same, but the mass number will be different. Okay. For example, when you take carbon, there are 3 isotopes of carbon. All these cases, the number of protons, so the atomic number will be 6. But for the first one, that is a stable isotope of carbon, the mass number is 12. Here the mass number is 13 and here the mass number will be 40. Okay, this is a radioactive isotope. Now you are able to see that in all these 3 cases, the atomic number or the proton number is same. Now what about the number of neutrons? Here the number of neutrons will be 6 because 6 plus 6 will give you the mass number 12. Okay, where 6 plus 6 is number of protons plus number of neutrons. Number of protons we already know. What about in this case? Here the number of neutrons will be 7 and here the number of neutrons will be 8. Okay, now take this case. Do all isotopes of the same have the same number of neutrons? No, right? Because in case of isotopes, what is happening? The mass number is different. So mass number is dependent on the number of protons and number of neutrons. Number of protons will be the same. Okay, that is atomic number is same in case of isotopes. So difference in mass number is created by the number of neutrons. Okay, number of neutrons are different. Number of neutrons are different. Now the fourth sub question, what is the number of protons and neutrons in uranium-92-238? This is another isotope. In uranium-92-238, the number of protons will be equal to 92. What about the number of neutrons? P plus N is equal to A. 92 plus N is equal to 238. N is equal to 238 minus 92, which is equal to 146. Therefore, the number of neutrons is equal to 146. So, we got the number of protons and the number of neutrons. Second example, complete the following nuclear changes. Here, you have XZA. This is the parent atom, parent element. It is undergoing beta emission. It becomes X1. We don't know what the atomic and mass number here is. Then it undergoes gamma emission. Again, we don't know. Then X2 is formed. We don't know what the atomic and mass number is. Then you have an alpha emission happening. There, X3 is formed. Don't know what is atomic and mass number. It then undergoes beta emission and X4 is formed. Okay. So, what is alpha emission? During alpha emission, what happens? The atomic number decreases by 2 and the mass number decreases by 4. During beta emission, what happens? During beta emission, the atomic number increases by 1, mass number no change. What about gamma emission? During the gamma emission, Z and A no change. Okay, now let's try this example. So here we have the parent atom XZA. It is undergoing beta emission. Then what happens? Atomic number should change. Atomic number should increase by 1. It becomes Z plus 1. What about mass number? Mass number no change. So it is A. Again undergoing emission. Here now it is a gamma emission. So gamma emission means only energy is being released. It is brought to the stable state from an excited state. So there is no change in the atomic number nor the mass number. That is Z plus 1 will be the atomic number and A is the mass number. Next it is undergoing alpha emission. Okay. During alpha emission what happens? Atomic number should decrease by 2. So here we have Z plus 1. Z plus 1 minus 2, which is Z minus 1. Okay, so here it is Z minus 1. What about the mass number? The mass number during alpha emission, mass number should change by 4. It should decrease by 4. So, A minus 4. Next, it is undergoing beta emission. During beta emission, what happens? The atomic number should increase by 1 and the mass number will be the same. So, mass number is again A minus 4. Atomic number is Z minus 1 plus 1, which is Z. So, finally, we have X4 Z A minus 4, which is formed from XZA by beta, 2 beta emissions and an alpha emission and a gamma emission. Okay. Now, what are the sources of these harmful radiations? The main sources of harmful radiation are, first one, radioactive fallout from nuclear power plants. So, we know that these nuclear power plants are a great source of electricity these days. Okay. But here what happens is, if there is some accident happening inside the nuclear power plants, what happens is radiations will be emitted in a high quantity, high amount radiations will be emitted from this. So, these radiation not only affect the persons who are working in these nuclear power plants or just in the vicinity, but people who are, or the organisms or living life which is at a long distance will also be affected due to these radiations. So, it is not only these radiations. So, these radiations by air current will enter into our body when we inhale. So, these radiations, we know the half-life will be high. Okay. So, they will start decaying inside our body and cause very harmful effects. So, first one, that is the radioactive fallout from the nuclear power plants. Even though it is helpful in producing electricity, but there is a harmful effect there. Next is the nuclear waste. We know that the fuel rod which is being used in nuclear power plants, after their use, after certain limit, they cannot be used further. Okay, they cannot be reused also, but still they will be emitting the radiations. Okay, they are radioactive. So, when you take these roads and just dump in some garbage or in ocean, what happens? Is it a good option to dump in an ocean? No, right? This radioactive waste or the nuclear waste cannot be dumped in a ocean. Why? Because it will be affecting the aquatic life. The plants and the other organism will be affected. So, the disposal should be done in a very conscious way. Okay, we should be very conscious while disposing it. So, now nowadays, in the olden days, it was mainly dumped in the oceans, but in these days, in containers, it will be stored. Okay, and then that is, you can just prevent. It is not that 100% good option, but still you can prevent the maximum emission from the emission of these radioactive radiations. Other sources such as cosmic radiations and X-rays from the sun and outer space, radiations will be entering the Earth's atmosphere. So, it contains a large number of high energy particles. Okay. Now, it contains both charged and uncharged particles. These charged particles get deviated by Earth's magnetic field. What about the uncharged particles? They doesn't get escaped out. Okay. So, they will be persisting inside the Earth's atmosphere and causing damage. It has many harmful effects. Okay. It can also cause damage to the DNA. That is, it can affect the DNA and it can cause cancers. Also, the high energy particle accelerators are also very harmful. Harmful effects of radiation. The radiations produced by nuclear reactions includes alpha radiation, beta radiations, gamma radiation, X-rays, and all these can enter into the human tissues in just 10 raised to minus 14 seconds and cause biological damages. Okay, so what are the biological damages? Let's see the harmful effects of radiation. First is a short-term recoverable effect. Okay. It can cause diarrhea, sore throat, loss of hair, nausea, etc. All these can be caused. It is recoverable and it is short term. Second is long term irrecoverable effects like leukemia and cancers. We have said that the DNA gets damaged and there will be change in the DNA which can lead to tumor and cancers. Next is the genetic effect. This affects the later generation of the person exposed to the radiation. So, these two is not affecting the later generation, but the genetic effect, it is affecting the later generation. Here the genes will get mutated. There is changes happening to the genes which can pass on to the future generations. Okay. So, both of these are mainly for people who are exposed to the radiation. That is, a person working in a nuclear power plant or in an atomic energy it is related to atomic energy. If they are working, they are exposed to these, directly exposed to these radiations. Okay, only then the short term recoverable and the long term irrecoverable effects will be in those persons. But when it comes to a third one, that is genetic effect, is not just to that person, but his generations can also have the effect. Now specifically we will be discussing about the harmful effects of X-rays. Exposure of pregnant woman to X-rays for a long time may affect the child in the womb. First we are discussing about the case of pregnant woman. This is why pregnant women are prevented from exposure to X-rays. So it can lead to miscarriages and also can cause mutation in the cells of the baby too. Okay, so physically and mental health of the baby may be affected. Second is, it increases the risk of cancer by 40%. That is, when you are exposed to X-ray radiation, we know that when you have some injury, you maybe you will be exposed to X-ray radiation, but if it is not done in a proper way, then it can lead to cancer by 40% of tumor, and the nervous system will be affected by 50%, and leukemia, it can cause leukemia by 70%, chances are there. Okay, next is the exposure of upper part of when the upper part of the body is exposed to the X-ray radiation, it can cause damage to the thyroid gland. Okay, one is thyroid gland, and it also can lead to a cancer. Okay, now the fourth point, the exposure of gamma rays destroys the cells of the body and affect the blood cells, gastrointestinal tract, reproductive and hair cells. So from these points we have understood that what are the harmful effects of X-rays. It is affecting a pregnant woman. How does it affect a pregnant woman? Then we have said how the nervous system will be affected. Then the thyroid gland, how it will be affected. Gastrointestinal tract, the hair cells, everything will be damaged because of continuous exposure to X-ray radiation if it is not done in a proper way. Now, the safety measures while establishing nuclear power plants. First one is ensure that the people working in it are not exposed to nuclear radiations. Even if there is a chance of accident, if an accident happens, the spread should be kept minimum. Okay, it should be ensured. Second, the nuclear reactor of the power plants must be shielded with lead and steel walls. So, this is in order to prevent the radiation from escaping out into the atmosphere. So, that can be prevented by using the lead and steel walls. We have studied about the penetrating power of the different radiations. So, lead can just prevent it from escaping out. Next, the third, the nuclear reactor must be housed in an airtight building of strong concrete structure. So, it can be prevented from that. Is it does not affect the earthquake, fire or some explosion won't affect it. Next is there must be a backup of cooling system for the reactor core. If there is a backup, one cooling system, if it doesn't work, the other cooling system will be working, and also it can be prevented from the overheating and melting can be prevented. Safety measures while handling radioactive materials, they should put on special lead-lined aprons and lead gloves. So, these lead-lined aprons and lead gloves, they will prevent the radiations from entering into the body of the person and help him to stay away from the radiation. That is, his body is protected from the radiations. Okay, so we know that lead, the alpha radiation or beta radiation cannot easily pass through the lead, but what about gamma radiations can pass? So, thick lead can be used. Next, they should handle the radioactive materials with long lead tongs. You should not go near it and use your long lead tongs should be used. Only then you have to handle the radioactive substances. The safety limit for each type of radiation is known. Therefore, care must be taken to ensure that no one is exposed beyond the safety limit. Okay, for that we'll be using something called film badges. Okay, from time to time it is checked to check how much of radiation, how much a person is exposed to the radiation. Next, the radioactive substances must be kept in a thick lead containers with very narrow opening. So, what does it mean? These lead containers, they will absorb the radiation, so the radiation won't escape out. Only through a narrow opening it will be escaping out. We know that alpha radiations cannot penetrate through lead. What about beta? Beta radiations can also, that is very less. Beta radiation can also not pass through the lead. We have studied the penetration power. What about the gamma radiation? So that when it is gamma radiation, you should use thick lead containers. Okay, only thick lead containers can stop the gamma radiation from escaping out. That is, this thick lead containers can absorb the gamma radiations. Now, safety measures in waste disposal of nuclear waste. So, radioactive material after its use, they will be known as the nuclear waste. So, these nuclear waste should be disposed. So, just dumping it in ocean or any other garbage, it is not easy. It's not that easy, the disposal of these waste. So, here what can be done is the nuclear waste obtained from laboratories. Laboratories is a source, then hospitals. What about the scientific establishments or some power plants? From all these places we will be getting the nuclear waste. They must be kept in thick casks and then they must be buried in the specially constructed deep underground stores. So you have to remember one thing, while disposing, that is when they are buried, they should not be buried in a populated area or in a residential area. It should be far away from the residential or populated area. So also in underground mines and all, they can be buried. Okay. So while disposing these radioactive waste, you should be very careful. Okay. It should not affect the life surrounding it. Now, what are background radiations? So, we can prevent from the radiations, but there is something called background radiation from which we cannot prevent ourselves. We cannot keep ourselves away from. Okay, the background radiations are the radioactive radiations like alpha, beta and gamma radiation, to which all are exposed. We all are exposed to these radiations even in the absence of visible radioactive source. Even though there is not any source, we are still exposed to these radiations. Okay, there are two sources. One is the internal source and the second is the external source. So first we will discuss about the internal source of these radiations. For example, carbon 14. We have said the different isotopes of carbon. Carbon 14 is a radioactive isotope. Then potassium K40 and the radium. These are present in our body. So they are an source of the background radiations. Next is the external sources. External sources, cosmic rays. We cannot prevent ourselves from the rays that come from the sun, cosmic rays. Naturally occurring radioactive elements such as radon is an example. Radon-222 is a naturally occurring radioactive substance. And the solar radiation, we are not able to prevent ourselves from these radiations. Okay, so we are exposed to these internal and external sources. Since the total of these radiation does not exceed a permissible range, we are safe. We don't have to worry about these background radiations. That's all for today. In today's class, we have discussed about the change in nuclei during an alpha, beta and gamma emission. We have studied the uses of radioactive substances, safety measures and the harmful effects. We have also discussed about background radiation. Hope you all enjoyed this session. I'll be back in the next session. Until then, stay tuned to Learnohub. Learnohub free hai, par best hai. Thank you.